Hi, welcome back. Our next topics for videos today is going to be finding the surface area of a sphere using spherical coordinates and also finding the volume using spherical coordinates. So I drew up a kind of diagram right here that kind of goes back to what I talked about in the last video, which was how we define our variables. In this case, I decided to draw a sphere next to it so that you can kind of see how this works. So again, we have our radius that goes from the origin to some point right here. And theta is a measurement of how far away that point is from the z-axis, from starting from the positive direction going to the negative z-axis. And phi is a measure of if you sliced the object in half, or you put a line through it where it has a constant z plane. In this case, we usually like to use z equals 0. Then phi is the measurement of the angles that are created by that bisection. So again, as a reminder, R can go from 0 to whatever the big radius is, to the radius of your sphere that you're creating when using spherical coordinates. Theta is a measurement of theta goes from 0 to pi, and phi goes from 0 to 2 pi. So that's going to be what we're being working with more this time as compared to last video where we were looking at something in 2D. This case, we're looking about something in 3D. So let's just get into it. Let's find the surface area of a sphere first. So I have this diagram here, and I want us to kind of work together to fill it in. So I have my origin set, and I have these lines that will help us find the surface area of this sphere that I drew. So let's start with what we're trying to accomplish. So we're trying to find the surface area of this sphere. And so just like the time before, the best way to do that is to find the area of a very small sliver of the part of the larger object, and then integrate over the entire surface. So that's exactly what we're going to do here. I created these lines so that we can make a little area to find our smaller area to integrate over. So that is going to be this little area right here. All right. So that most resembles a rectangle. So let's call this DA, and DA looks like a rectangle. So DA looks like a rectangle. And so we know that a rectangle has an area that looks like this. It has a length times a width, and that is the area of a rectangle. So what we want to do is find the area of that rectangle and then integrate it over all of the rectangles of the sphere. So the first thing that we need to do is find what the length is and what the width is. But we need to define our few variables first. So let's start with our radius. So since we're going to be doing a surface area, we don't have to worry about the change in radius yet, because we're just looking at whatever is on the surface, and whatever is on the surface has the same radius. So I'm going to say that we have this radius and that radius. So those two dotted lines that I drew have the same radius there. We could say that it has the same radius there. It has the same radius because we're just looking at the from the origin to the surface, so it has the same radius. Cool. So now let's look at our next components, our next coordinates, which is theta and phi. So I kind of drew these slices to represent our change in our variables. So let's start with theta. So I'm going to draw some dotted lines from the blue section, and I'm going to draw it like that and like that. And just remember that theta is a measurement of how far away we are from the z-axis, going from positive to negative. So we can draw it like that. So let's say that this one here is 1, this is 2. So just like before, the dotted line labeled 1 has that angle of theta, and number 2 has that angle theta plus another change in theta that we don't know yet. So we can say that this change right here is d theta, just the change. We don't have to worry about what thickness this is yet. We're just looking at that is the angle theta. D theta is whatever that from here to here is. So now let's look at phi. So phi is measured from if we sliced it in at z equals 0, that entire region that we would see when it was sliced. So I'm going to draw some dotted lines from here to here in the purple section. And so we know that theta, or phi, sorry, goes from that way. So if we have these two, this line that goes like this, it has one angle phi that is at 1, and at 2 it has some angle phi plus some other d phi that we don't know. So this is equal to d phi. So now we have a good understanding of our coordinates. So now let's look at our length and our width. So let's say that this is our length and that is our width. So we want to find what that is. So one more important thing that I want to label here is this value right here. So that little black line that I just drew. So it's a little bit difficult to see. It's getting a little bit messy, but hopefully you can kind of see what I'm trying to do here. So if you look at how I drew this, we can kind of imagine seeing a triangle that is right here. I'll try to make this as bold as possible. Right there. So we can see that this has some hypotenuse, and it has a right angle right here, and it has some z component to it. And so I want to see if I can label this a little bit better. So just like before, if we're going from the origin to any point on the sphere, which is exactly what we're doing, this value right here must be r. And again, this value here is theta, right? So it has some r and it's being translated an angle theta. We want to find what this value is right here because it'll be very helpful to us. So that little right here, that little star, if you can kind of see, it's going to be r sine theta. And that is because we have theta is defined as the opposite over hypotenuse. So our hypotenuse is r, and we're trying to find what this value is right here with the star, and that is our opposite value. So theta is in the corner, and the opposite side is that starred side that we're trying to find. So our starred side is just r sine theta. So let's keep that in mind, and let's find our length and our width. So now I'm going to kind of clean this up a bit. Let's see. Okay, so now that we know that that is our r sine theta, now we can start looking at our width and our length. Okay, so I kind of redrew this a little bit so that you can kind of see how this is working a little bit. So we decided that that starred length that I drew is r sine theta. So I know it's a little bit difficult to see, but imagine the strip is kind of, it is wrapping around the sphere. And so the distance that I labeled with the star is kind of like however far away you are from the z axis. So it is not from the origin, because from the origin to where we are is r, but we wanted that little distance there because we want to find out what this L is. So we know that this distance is r sine theta, and we know that the change from here at 1 to this change 2 is d phi, because we labeled it down here with the purple. So from 1 to 2, we have the length, which is where we start at, which is r sine theta, because our r is constant and sine theta is constant at this point. And then from 1 to 2, our phi changes. So our length is r sine theta d phi. Okay, cool. So now let's do the width. So we have r. So we're at the same r, but now we're constant on the phi purple right here from 1 to 2. And now we want to find our width. So then we look back at our blue shaded region, and we see that we're only changing our theta direction. So now our width is defined as r d theta, which is very similar to what we did in the first video with finding a circle. So now we have our length and our width. And now to find the area of a one rectangle, which is our dA, we say that it's just equal to the product of those two values. So I'll write it over here. So dA is equal to length, which is r sine theta d phi, and our width is r d theta. So let's combine our r's and simplify. So we're left with r squared sine theta d phi d theta. So that's the area of our one rectangle right there. So that's what dA is equal to. It's r squared sine theta d phi d theta. But now we want to find what the entire surface area of the sphere is. So now we're going to do a double integral. Well, this time we're going to do a triple integral. So hold tight. We're going to do our triple integral. So we have three terms now. We have our r squared. Let's just say that it goes from 0 to r to just kind of drive home the fact that this is just a constant value. Nothing's changing from 0 to r. And now we have our theta. So for theta, just like before, our theta goes from 0 to pi. So it goes from the positive end of the z-axis to the negative end of the z-axis, which is just pi radians around. So that goes from 0 to pi. And our phi value, just like before, goes from 0 to 2 pi. Okay, so now we're going to put in our value. So r squared sine theta d phi d theta d phi. So now let's put each of its values in its respective respective integral bounds. So we're left with 0 to r squared, 0 to pi sine theta d theta, and 0 to 2 pi d phi. Okay, so now we have our integral set up. Just a reminder, r is constant, so we have we're just left with r squared because there's no dependence on r. There's no dr in our integral, so it's just r squared. The integral of sine theta is negative cosine theta, and we're evaluating it from 0 to pi. And the integral of d phi is just phi, and we're integrating it from 0 to 2 pi. Those are the bounds. So going back, r squared, negative cosine pi minus a negative cosine 0 times 2 pi minus 0. So cosine pi is a -1, but we're taking the negative of a -1, which is a +1. So we have r squared 1, and then minus cosine of 0 is 1. We're taking the negative of it, so it's -1. And we add those two together, and we have that 2 pi, because 2 pi minus 0 is 2 pi. So we have r squared, 1 plus 1, 2 pi. So we're left with r squared 2 times 2 pi, which is just 4 pi r squared is the surface area, and that is the correct answer. So you can look it up. The surface area of a sphere is 4 pi r squared. So that was the surface area of a sphere, which is very helpful. So now you kind of understand where that's coming from when we're calculating electric fields. But let's go one step further and let's do the volume. So again, I have our cylinder or a sphere here. We can go in and plug in our values that we already know that we just did. So that is our d theta, which is this value right here. This value right here is d phi, like before. And we now, instead of finding just the area of our sphere, we want to find the volume. So now we're going to be taking a little sliver like this, and we're going to find that volume now. So what this kind of looks like is the kind of looks like a pyramid. So what we're going to do now is we're going to do the exact same thing, but we're going to add our height into it now. So again, this is our length, this is our width, but now we want our height in it as well. So again, our length is just our, again, and this is this value right here that I defined from before is just r sine theta. If you're confused, just go back and kind of rewatch why I defined it as that. And our L is just r sine theta d phi from that purple region. Our width is just r d theta because we're at a constant r from here to here. And what's the only thing that's changing is our d theta. But now we want to add in our volume aspect of it. So our height now, if we're taking this little, kind of looks like I know I said pyramid before, but it looks kind of more like a rectangular prism if we just had it stuck down there. It becomes that this value here is our dr. So our height is just dr. And our volume of a rectangular prism is just length times width times height. So now our shaded region is this right here. So now we want to integrate over every single little volume of that. So our V, our dV, let's call that our dV, is just r sine theta d phi times r d theta times dr. So cleaning that up a bit, we have r squared sine theta dr d theta d phi. Now we want to find the full volume of our sphere. So we're going to use our bounds and integrate over our volume, element that we just found. So we have from 0 to r squared, and we have a dr now, so we're keeping that in there. And we have a sine theta d theta, and we know our theta element goes from 0 to pi. And our phi is still just d phi, but we know that it goes from 0 to 2 pi. So now let's solve this integral. So now we have a r squared term, and we need to keep that in account. So the integral of r squared with respect to r, or r squared dr, is just 1/3 r cubed, evaluated from 0 to r, which is just what we wrote there. So I'm going to leave that out. And then we have the integral of sine theta d theta from 0 to pi. So the integral of sine theta is negative cosine theta, evaluated from 0 to pi. And the integral of d phi is just phi, and that's integrated from 0 to 2 pi. So we already know that that negative cosine theta from 0 to pi is equal to 2. So I'll say equals 2. The integral from phi from 0 to 2 pi is just 2 pi. But now we have our cubed term. So now our final answer is the volume of a sphere is equal to 4/3. So 2 times 2 pi is 4 pi, but 4/3 pi r cubed. And that is our final answer. And that is the volume of a sphere. So I hope this was helpful. If you want a challenge problem, you can try and do this with cylindrical coordinates. So instead of having a theta term, instead of having our theta term, we just have a z term instead. So what that would look like is something like this. So we have our cylinder here. We still have our radius term and our phi term, which goes like that. But now instead we have this distance z. So that is our new terms. So if you want to try it out, you can try that instead. But I hope this was helpful, and I will see you next week.